Okay, we've got another fairly simple one. I think this one's mainly to test your linear interpolation skills. Okay, so we've got water in a tank exists as a saturated liquid at 670 kilopascals. What is the water's enthalpy? Alright, we're going to go ahead and look at the steam dome so we make sure we know what we're looking at. It doesn't really matter if you use a TV or a PV diagram, but since it's given us pressure, we're just going to go ahead and use that. You could use a TV diagram and just keep in mind that the line that you draw is this given pressure. Okay. So we've got a water in a tank exists as a saturated liquid. Okay, where does that put it on this graph? Well, a saturated liquid is a liquid that's just about to become a mixture. So we've got the liquids over here, we've got the vapors over here. We're about to switch into the steam dome. So the point that we want is going to be on this line. Don't really know where it is vertically. Doesn't really, well, technically we do because we've got this. But just to show the concept, it doesn't particularly matter. Okay, so this is our P, which is 670 kilopascals. What is the water's enthalpy? Okay, so we know that the enthalpy is represented by H, but when we look at the table, we have, give me a second to get the right table. We want A4, maybe A5, because we have known pressure. This is temperature, so let's go to A5. Alright, our pressure, okay, yeah, we're on the right graph. Alright, if you look here, I don't know how well you can see that. Let me, woo, a little too much. Here we got 3 different enthalpies. So which one do we want? Well, we see the subscripts HF and HG. This is the HF is of the saturated liquid. It stands for heat of fusion, I think. Enthalpy of fusion. I assume that's what it means. And then we've got the enthalpy of the gas. We're obviously not interested in this one. This one is just simply the difference or the enthalpy in the steam dome. We don't care about that. We only want the enthalpy of fusion because that applies to the saturated liquid. The value that we want is for 670 kilopascals. So here we can take a look at it and we see that there is no 670 kilopascals. So let's go ahead and record. We got 650 kilopascals and the value for that is 684.08 and the units is kilojoules per kilogram. Okay, so 684.08. That's the wrong button. 684.08. I'm really bad at remembering numbers. See, I've already got it. It's 684.08. Okay. 0.08 kilojoules per kilogram. And this is kilopascals. This is our P1. Our P2. This is our HF1. Our P2 is going to be the next step down, which is 700 kilopascals. And our HF2 is in the table. Let's take a look at it. HF2 is going to be 697.0. Alright, we're going to use linear interpolation, which means that we're going to have some function of y equals some slope times x plus some constant b. Alright, in this situation, our slope, excuse me, not our slope, our y is the thing that we're looking for. It's the enthalpy. So we're going to say that the m is the rise over the run. The rise correlates to the y value. So we're going to say delta H, delta HF specifically, divided by delta P equals our M, and that equals This is equivalent to 0.2584. Alright, so now that we've got our M, we still need to find our B, but in order to do that, we've got 4 unknowns here, but 3 of them are known. We've got our M, we can take either one of the X's and its corresponding Y. Alright, so I'm going to take 700 just because these numbers are a little bit prettier. So the 700 value is 697.0 equals 0.2584 times 700 plus B. That's going to give us our B value, which is 516.12 is our B. Alright, so now we want to find the actual HF for this value P. Alright, so that's 0.2584 times 670 kilopascals plus 516.12. Alright, our final answer is going to be 689.248. And this is the enthalpy. Specifically in units of kilojoules per kilogram.